Hello and welcome back. So let's go ahead and continue this Hare tutorial series. I would like to say thank you to my subscribers. If you're catching this later after an upload, there obviously won't be any missing time between uploads, but I do apologize that it has been a while. I will try and get on a more consistent upload schedule. But I really appreciate all of you. And really quick, I have a little bit different setup. Um, so if I run fast fetch, you can see I'm on void and I'm back on sway, which is like this is like my original setup when I first got into Linux and got comfortable using Linux. And I'm also trying a different screen recorder, which is WF Recorder rather than OBS Studio. So let's see how that works out. So let's go ahead and jump right in. So for this part of the tutorial, you should be on Hare Basics, Functions and Parameters. And go ahead and copy this or type this into your text editor. And let's go ahead and read over this. So the sample program shown here is a bit more complex, and we're going to examine it in detail over the next few headings. This program prints a greeting, then prompts the user to enter their name, then greets the user by name. There's a lot to unpack here, but we'll get started by looking at the use of functions. Now, this is really basic. I'm sure most of you might be familiar with this little paragraph here, but let's just go ahead. A function is the basic unit of executable code in a Hare program, which defines a step or series of steps for the program to perform. Functions can call each other to deputize various tasks, such as relying on FMT to format text for printing. So obviously here we're calling ask name, here we're calling greet. This is a function call. Functions may accept a list of parameters by placing them between the parentheses tokens when declaring the function. Greet accepts a string parameter, so that's right here, which it names user. Functions can also return values to the function which calls them, such as askName, which returns a string. That's right here. To return a value from a function, you use the return keyword. Our main function makes use of the return value by storing it in a variable and passing it to greet. So that's right here. We're declaring this as a const variable, which is a runtime constant. So when this returns, this is just a little command line program that reads from standard input and converts it to a UTF-8 string, passes it to the print format line function, and prints it to the output. So note, many code samples in this tutorial make use of concepts which are introduced later on. If you're unsure about how something works, don't worry, it will be explained later. And I will certainly try my best to explain things as we go along also. So let's go ahead and run this program and see what it does. We get a basic idea from reading the code, obviously. So we'll say Hare run, pass in the main file, and it prints a prompt, hello, please enter your name. And it greets us with hello and then your name. So excellent. This next part of the tutorial will cover all of this code and break it down and see what it does. Okay, so to continue on, you should be on this portion right here, a closer look at bufio readline, and this is really kind of the bread and butter of this little program, what's going on right here. So let me go ahead and pull that up. Okay, like askName, many standard library functions can return values. Bufio readline is an interesting example of this. Now, bufio is a common abbreviation you'll see in programming, right? So we're importing the module here, and it just means buffered input-output. So we can read the documentation for this function in our terminal by running the haredoc bufio readline command. Try this now. Okay, so let's go ahead and open this up. Haredoc bufio readline. You can see it says it reads a slice of bytes until a new line character. New line it, so that's when you press enter. New line itself is not included, but it is read from the handle. So that's kind of interesting because it seems to be suggesting that it kind of flushes that new line character out of the input buffer. So if you're familiar with scanf and C, which you generally should not use, but if you're familiar with that, you know that under certain conditions, that new line character is stuck within the input buffer and you have to do something like call getchar or flush it out some other way before you can call scanf again. Or else the next time you call scanf and try and put the read in value into a variable, is going to pull out that new line character instead, because sometimes it will stay in that buffer. So it appears to sort of, what it appears to be saying is it flushes that new line. And it says the return value must be freed by the caller. Now we haven't dealt with freeing memory yet. So this part of the tutorial does not want us to worry about that. We will come to a point where we will deal with that, but let's not worry about it now. Technically, for now, we're going to have a memory leak. And this is why it's important to use HareDoc when you're writing your programs. That's what this portion is really going to cover, is this HareDoc command, so that you can look up all your functions that you're calling. You should be looking up all your functions that you use in a Hare program. Okay, because they're very simple, but you have to look them up, and some might allocate memory dynamically. So let's go ahead and return back to the screen. Okay, so this function signature, the combination of its parameters and return type. So if you're not familiar with what a function signature is, that's this right here. It's a definition. It defines everything about the function, obviously except the logic. Is a bit more complex in that it can return one of several kinds or types of values, forming what's referred to as a tagged union. Now, if you're not familiar with tagged unions, this is a tagged union, and this is the return value of the function. And what this is saying is this can return a slice of bytes, end of file, or IO error. Don't worry about what they are specifically for now if you're not familiar with a tagged union. What a tagged union is, right? Think of this like an exclusive OR. So this can be this, or this, or this. But it cannot be two of them or all three. It can only return one of these types. And that's what a tagged union is. You can basically say, hey, here is a value, right? Think of it as an L value. And you can say this value can be one of these several types. Well, that's what's happening when readline returns. It's returning this tagged union, and it can return one of these values. So the value is going to be one of these types. And, tagged unions are a sum type, which is an algebraic data type. If you wanted to look that up, you could just look up tagged union. They're also called discriminated unions or variants. It's a very common feature in functional languages, so like Haskell, OCaml, for example, and it's very common to see these used with pattern matching. So this is like a functional feature that's making its way into procedural languages, and I love this paradigm of programming. I'm like really spoiled. It's very hard for me to use exceptions anymore. I like errors as values, errors as types. So let's go ahead and continue on. Hopefully that's clear. The more you use Hare, the more comfortable you will become with some of these concepts. Like for example, before I got into Hare, I did a little bit of OCaml. There's this really great course. I'm trying to remember the person's name. They're a professor, and they do this really long series on OCaml. You can find it free on YouTube, and there's a book. But it's actually, they don't use any object orientation. It's just kind of, pure functional. So it was a little bit familiar to me before I came to Hare, but not really. right? Here is where I really kind of cut my teeth on tagged unions and pattern matching. So the one we're interested in is U8. This is a slice of U8 unsigned 8-bit integers, which is a slice of bytes containing the line we want to read. Now, if you're not familiar with what a slice is, just think of it like an array. Think of it as a view into an array. Okay, so think of it as a dynamically resizable array. Okay, that's to not overcomplicate things. That's basically what a slice is. It's an array that can that you can add and delete elements from. As to where that's a slice. As to where an array is almost always, depending on the language, it's almost always a fixed size. Okay, it can also return IO end of file, which indicates that the end of the file was reached, or IO error, which indicates that an IO error occurred. Run the haredoc IO error command and note the error flag, which prepends the signature, which signifies that IO error is an error type. So let's go ahead and try that. Haredoc IO error, and you can see this is a type, so we're defining it. Well, this is in a standard library. It's defining a type named error, and it's a tagged union, and it can be errors error, this is the errors module, under red, or no mem, and this means that it failed to allocate memory. So you can see the error flag here, it prepends the type, and that's how you know that this is an error type. So for example, when you call a function, here's a function, and you were to put the error assertion operator when you're calling a function, that's the error assertion operator. When it prepends a type, it tells you that it's an error type. So hopefully that's not confusing. Okay, encountering the end of a file is not considered an error. The exclamation point in our program is an error assertion operator, and it's referring to this right here. Which deals with the error case, as we described before, leaving a slice of bytes and IO end of file remaining. Now, a slice of bytes is a very common, sort of a stream, for programming. If you're not very familiar with streams, the way input buffers work, this is a very, it's really the only way, well, okay, I'm not going to say the only way, but, it's the simplest way to represent a stream of input data, for example. And then you have to parse this somehow into whatever format that you're interested in. Okay, so to address this, we use the as operator, which is right here, to interpret the value as if it were a slice of bytes. This is called a type assertion. So you can see here in readline we're passing OS standard in. If you want to look this up, go ahead. This is just standard input. This is your standard input stream. So by default in a Unix environment, your program will have 3 streams defined, and that is standard input, standard output, and standard error. So this is just your console. This is just a standard input stream. It's like reading from the console. Okay, like other assertions, the compiler will check your work and, if proven wrong, will cause the program to crash. You can simulate this by pressing Ctrl D in your terminal emulator instead of entering your name. Feel free to try that. You will crash your program, and that's this in operation right here. Okay, so a key takeaway from this should be the haredoc tool, which you should use liberally as you work with Hare. Try to use it to learn about the other standard library functions we're using in this sample, such as strings from UTF-8. You can also use it to browse the modules themselves. Try haredoc FMT or haredoc strings. So that's what it is really trying to get across here in this example is the hare command, and you should be using this like it says, use it liberally. Okay, you're going to be using the hare command all the time. It's a great way to look up documentation, standard library functions, and types and things like that in your command line while you're working with Hare. Now, normally what I like to do, I have a dual monitor setup. I don't have it running right now because, you know, I don't know, not the resolution, but it wouldn't look right on if I were to record a dual monitor setup. There'd be, extra space on the top and the bottom. So I'm just using a single monitor setup. But what I like to do, I have a dual monitor, and on one monitor I have my text editor, and on my second monitor is where I like to have my documentation up so I can just kind of glance over and it doesn't like interrupt my workflow. So let's go ahead and look up strings from UTF-8 and see what's happening here, okay? Let me clear my screen. So you can see it says it converts a byte slice into a string. The return value is borrowed from the input. If the slice contains invalid UTF-8 sequences, encoding UTF-8 invalid is returned instead. So this would be the top level module, this would be the submodule, and this is a type, an error type. So I'm not going to go down too much of a rabbit hole of looking these types up. Please feel free. So what this is saying is from UTF-8 takes a slice of bytes, right? That's right here. This name, when we call bufio readline and we type assert on it as a slice of bytes, that's what this is. Okay, we're using type inference here. Now we're passing it to from UTF-8 because it is a slice of bytes. So this takes a slice of bytes. And what this does is it returns a valid string, because strings in here are UTF-8 encoded. And if you're not familiar with UTF-8 encoding, it's getting into detail with it is obviously beyond the scope of this video. There's a really good video by a C programmer. I think his name is Nick Barker. You can look that up. I think it's called UTF-8 Explained Simply, or you can just look up the standard. There's a lot of documentation about UTF-8, but essentially, UTF-8, first of all, is backwards compatible with ASCII, which you might be more familiar with that. Let me go ahead and switch back here. So it's backwards compatible with ASCII. So the first 127 or 128, whichever it is for ASCII, those are valid UTF-8 characters. Now, UTF-8, some of the characters are multiple bytes in width, so they're multi-byte characters. So if you were to try to like iterate over, a multi-byte character string in UTF-8, and you would probably get an invalid character because again, some of those characters are made up of multiple bytes, as to where in ASCII it's just a single byte. Well, technically 7 bits, but a single byte. So, and in UTF-8, a character is called a rune. It might seem confusing if you go looking it up. What's a rune? Okay, a rune is nothing more than a character in UTF-8. So if you're familiar with C, you have the char type. Well, that defines a character, except it's in ASCII. It's ASCII encoded. So a rune is just UTF-8 encoded character. And again, a rune, right, or a character in UTF-8 can be multiple bytes in width, and that's why we have to that's why we have to take our byte slice and encode it into a valid UTF-8 string, and we're returning that. So data type str in here is a UTF-8 encoded string. Okay, and if you were to run the haredoc command on one of these top level modules, it's going to put you in the very top level of the module. So let's go ahead and let's just say haredoc strings. So now we are in the, this is the very top level module of the strings module, It's very verbose, okay? Um, you can, so I'm pressing spacebar, it goes by page, but this is very verbose. It has all of the documentation for the functions. You can see these are functions, join. It has all of the types, if I can find those. Okay, type end is of type void. It has submodules. So this is the, if you type in just HareDoc and then whichever module, it's going to put you in the top level module. So you should be using HareDoc liberally, get used to it, look around. You're just going to have to really experiment with this language because at the moment there's this tutorial and then there's the Hare language spec, and that's it. Now again, I'm working on a book. Maybe my next video I'll do a quick update on how that's going. But really my book started as kind of, documentation from me learning the language. And I was like, you know what? I want to put this down in kind of a formal manner and give people a resource so that, they know where to go and what to do if they're stuck. So that's the HareDoc command. We should be using it liberally, and we're going to be using it as we go along here. So that is this program so far. Let's go ahead and continue to the next section, which as you can see is using const and let to define variables. Okay, using const and let to define variables. So you should be on this part here, and go ahead and either copy or type this into your text editor. And admittedly, this is can seem to be kind of a complex example with all of these standard library functions that we're calling. But let's just step through this. Okay, this sample is designed to illustrate a few common ways to use variables in Hare with the const and let keywords. So here's const. This is a constant variable. This cannot be changed. Here's let. These variables can be changed. When declaring a variable, you must provide the initial value with an initializer, such as a constant value like 42, which we all know is the answer to life, the universe, and everything, or an arbitrary expression like a function call. So all variables in Hare are required to be initialized at their point of creation. You cannot create a variable in Hare without initializing it to a value. And that's designed to eliminate undefined behavior and errors in your program. A variable declared with const cannot be modified after it is initialized, but you can modify let variables with the assignment operator. So const is a runtime constant. If you watch the language overview, this is a runtime constant. Def is a compile time constant, and you can put that into arrays, for example. Let me not overcomplicate this example. So what we're doing here, let's go ahead and run this first, right? First things first. Okay, and it reads the file, and it gives us the first 3 lines of the program. And it would appear to be the first 5. What am I missing here? Okay, so this is being printed out by here. Sorry about that. This is from example A, okay, and that's right here. And then this first 3 function is printing out these values. So let's go ahead and open this back up. So what's going on here? OSOpen opens the main file, right? We're saying main.ha. If you wanted to create a file in your directory and name it whatever you'd like, you can do that. IODrain pulls from this source. Now, you see we're using variable shadowing here, okay? However, though, you cannot modify a const variable. You can rebind it by creating another variable with the same name, and that's what we're doing here. Notice that this has the same variable name. We're redeclaring it, right? Because const or let or def is a variable declaration. So this is not a reassignment. This is a redeclaration. When rebinding a variable, you may also change its type. In this example, source refers to an IO file, a slice of bytes, a string, and a string slice in that order. This is a useful pattern for building up a variable from a series of intermediate values of various types. This technique is more generally called shadowing the variable. Now, some programming languages will not let you do this, okay? And normally you'd have to say, okay, this is going to be source, this is going to be, and you'd have to, you know, um, come up with a name for every one of these different variables. Now, which we all know is one of the hardest problems in programming besides off by one errors. So after this new declaration, this variable is invalid, right? Because this L value points to this source here. So it invalidates the first variable. You're redeclaring it. And what all of these do is what we're doing is we're opening the file, we're reading from it, we're converting it to UTF-8, we're splitting it into a slice of strings, which then gets passed into this function here, first3. And you can see it takes a string slice. That's what's happening here. And then it prints it out 1, 2, 3. So if we look at OS Open, this is your standard file utility. So like fopen and C, okay? And this, it takes a string, which is a path, right? So this is our path, and we're already in this directory. Okay, and it defines a read-only flag. Now this is default a default variable, so this is passed in automatically. You could change this if you wanted to write only. I doubt it would let you while you have it open. And it can return a valid IO file, right, which is a file handle, or an error. Okay, then what we're doing, let's look at IO drain. Reads an entire stream into a byte slice. The caller must free the return value. Again, the tutorial does not want us to worry about that now. Note that this function will never return if the handle is infinite. So if you're reading an infinite stream, it's not going to return. So here's your file handle that you're passing in. You see we're taking it here and we're passing it in here. So we're passing in a file handle, and it can return a byte slice or an error, which is going to be I believe this is what it's going to be. Now it might be in any case though, this is a tagged union of all the error types. It's in the errors module, and you can see it has the error flag. Here's the error flag. So this is not at the end of a function call. It's not a postfix. This is a prefix. It's prepending the type. These are types. It's not a function call. It's defining a tagged union. So error is a tagged union of all the error types in here. Now, most, if not all of these, are going to also be tagged unions, or some of them at least. Okay, and then we're passing it in from UTF-8. So again, just like we did before with our command line program, this is going to return us a slice of bytes, and we're passing it into strings from UTF-8 to get a valid UTF-8 encoded string. Now notice that we're using the error assertion operator here on all of these. Okay, so all of these functions can error. This would be a perfect example of where you're really going to want to do error handling with some pattern matching. In reality, you'd probably want to wrap all this in a function and either handle the errors in place or propagate them up the call stack. We're going to worry about that later, but it is something you have to be aware of. We're using the error assertion operator on all of these. So let's look at strings.split and see what that does. See, we're passing in our source, which is coming from UTF-8. So this at this point is a valid UTF-8 encoded string, and we're passing it to string split, and we have a delimiter here, which is the new line character. And you can see it splits a string into tokens delimited by delim, which is this right here. Okay, this is our delimiter. The caller must free the return slice. The strings within the slice are borrowed from in. The caller must ensure that delim is not an empty string. So here's our delimiter. It has to be a valid string, right, which is right here. It's a valid string. And it can return a slice of strings or no mem. You see it can fail to allocate, and that's why it has to be freed. So kind of a complicated example. When I first looked at this tutorial over a year ago, this example in particular really intimidated me. But I can promise you it just takes time and effort to learn programming. It's not easy. I'm not going to claim that learning systems level programming is easy. There's no quick way to do it. You just have to sit down and work your way through things one step at a time. Try not to overwhelm yourself. Try and focus on one or two concepts you're trying to study. And what I like to do is I study a concept like all day, spend 24 hours studying something rather than being like, okay, well, I understand that, and probably you do, and being like, okay, I'm going to move on. Really, really kind of, put that into your long-term memory. Um, that's kind of what I like to do. So, and then we're passing this once we have a string slice, which this takes here. First three takes a string slice, and we're just printing it. Okay. And this is lines. You see, we're just defining this here. So this is arbitrary. We could name this whatever we wanted to. So again, we're just reading a file and printing out the first three lines of it from here. Now, if we wanted to, okay, let's continue on with this, and then we'll play around with this the OS open function real quick. Take note of the syntax as well. Each of the bindings in example A, so that's right here, use type inference. You can see you don't always have to use an explicit type annotation in Hare, which is really great. Now, some people like to use explicit type annotations. I personally do, but they're just not practical really under every circumstance. It just adds a lot of verbosity to the code, but everyone has their own opinion on this, right? Some people are very passionate about it. To annotate or not annotate your types. I get into this in my book in a little bit, right? Really, it's personal preference, but idiomatic Hare programs generally do not use explicit type annotations. Okay, you're going to see mostly type inference. But the advantage of using an explicit type annotation is that it's a form of self-documenting code, and it can help to prevent errors at compile time and rather than runtime. So so take note of the syntax. Each of the bindings in example A use type inference in which the variable is automatically assumed to be the type of the right hand side of the statement. The let examples demonstrate the use of an explicit type int. So that's right here. This is an explicit type annotation. Okay, let I be of type int and equal this value. You see you can define multiple variables on the same line. This is separated by a comma. You could just as easily place this on its own line. This is generally not a good thing to do, but I think it's just showing the example that you could do this if you wanted to. In some cases, it may be necessary or helpful to state the type explicitly. This can be done at your discretion or when the compiler asks you to. So, and then here we're using the print format line function. This is the format string here. This is where your variables get formatted and plugged into. So I gets plugged in here, j gets plugged in here, I plus j is right here. Now we're reassigning because we used let to declare j. You can reassign a new value to it. This is not the same thing as variable shadowing. See, when we're declaring a new variable here, this one is discarded and we're declaring a new variable of the same name. This is variable shadowing. Here this is just a simple reassignment. So we're saying j is equal to I. Okay, and then we're doing the same thing, printing I plus j. So let's go ahead and run this program again real quick, hopefully understanding what it all does. And then I'll come back to this and I want to show you a couple of things. Okay, so the one thing that I wanted to do was replace this, the file that it's reading, to something else. Let's look at some explicit type annotations first, which I have here. Okay, I haven't finished this. So basically, if you wanted to explicitly annotate your types, let's look up OS open. Okay, so you can see that it's going to return on a valid return, it's going to return IO file. So if you want to explicitly annotate this type, it's going to be IO file. Same thing with IO drain. Let's look that up. And you can see on a valid return, it's going to return a slice of unsigned 8-bit integers. So you could annotate the type like this. Same thing with from UTF-8, it returns a string, type str, and let's look up strings.split. Okay, it returns a string slice. So let's go ahead and annotate this type with a string slice. Now, when I run this program, you can see it runs just fine. Now, again, Hare programs, idiomatic Hare programs, do not generally annotate types like this. That's one of the sort of built-in features of the language, is that you have explicit type annotations, right? So you don't have to do that. Now, the one thing I wanted to show you real quick is we could, if we wanted to, read a different file. So let's say text.txt. Okay, let's just say that. And I'm going to delete all of this from this function so that we're just working with this part here. Okay, now we're going to open a file named text.txt, and same thing. We're going to read the first 3 lines from it. So go ahead and put in text.txt or whatever, name it whatever you'd like. Okay, and let's save this program. And then I'm going to make a file called text.txt. And we'll say, hello world, my name is Empathy Monster, how are you? Okay, now let's save this. Now let's run our program, and you can see it reads from, okay, well, that's a prompt. So, hello world, my name is Empathy Monster, how are you? And it reads the first 3 lines from that's what this function does here. Print, print, print. We could add this and print more lines. We could add more lines. So that's what the OS open function does. It just opens a file, and then you would do whatever you need to it. By default, it opens it in read-only mode. Again, if we were to look at, here it is right here. So you see it has a default permissions flag set, which is read only. And let me just make sure I covered everything in this part. Yes, I believe I did. So that's it for using const and let to define variables. Excuse me. Let's go ahead and move on to more about types. Okay, so to continue on, you should be on the more about types section. And if you are generally familiar with programming, this part is going to be pretty simple, at least hopefully. If not, that's okay. Let's go ahead and look at each one of these. So these are explicit type annotations. We're saying these are let bindings. So these are mutable values, and you can see how you can do multiple assignment statements in sort of like a factored style, let bindings. So these are explicit type annotations. This is int, which is a signed integer. Here's an unsigned integer. So if you're not familiar, this can be positive or negative to a certain limit. Unsigned integer, which is only 0 and positive. Unsigned 8-bit integers, which is 8 bits in width. A single byte. F32, it's a 32 byte floating point. 32-bit floating point, excuse me. And there's also F64, which is 64 bits. It's wider. It can hold a larger number of characters, of decimal places. Now you can use type inference from a suffix. Now by default you have default types in Hare. So if you were to move this I, this would just be a regular int. Here's a U for unsigned. Here's U8. So you can use a suffix to determine the type as well. Here's some other types. Type string, right, is an explicit type annotation. This is a tuple, tuple, tomato, 42, 24, and to access this, we will look at how to access this later on. If you're not familiar with tuples, this is a product type. So when you define a tuple, it has to have both values. So this is not like a tagged union. Okay, it has to define each value for your tuple. Here's a struct. Now we're starting to get into some of the bread and butter of C-like languages. So we're declaring this is a struct, let x be struct, and this is x and y values. And here we're defining it also. Okay, so we're plugging the values in. And this is an array. This is how you would define an array. You notice that we have an explicit length defined in this array. The length of your arrays have to be known at compile time. Now I'll show you a way to avoid magic numbers. You generally don't want to put a number in here. You want to define a variable with, say, like def, right? So we could say def, and let's just define it to be we'll say length, and we'll say equals 4. Okay, now what we do is we plug this in here. Okay, and now, so say you have to refactor your code, you're just looking for your def variables, which maybe you define at a top level or something like that, instead of having to go in and change the length of every single one of your arrays. Now the type of an array is the length of it determines part of its type. So you see we're just initializing this here, and this is a slice. You can see there's no length variable in here. Now a slice defined like this has to be freed. So technically this would be a memory leak. So let's go ahead and run this program, and it's not going to do anything because you can see we're not importing the FMT module to print anything to the screen, right? So let's just make sure that this compiles, and it does. So Hopefully that's pretty self-explanatory. We will start using some of these in the next lesson. So here's a small non-comprehensive sample of some other types supported by Hare. Hare supports signed and unsigned integers of various sizes. Signed numbers are able to store negative values as well as 32 and 64-bit floating point types, which can store a fractional component. The exact type can be inferred from context, as in the first example, so that's right here, using explicit type annotation, okay, or specified with an appropriate suffix, so that's right here. Note, if you are not already familiar with binary and floating point arithmetic, you may be surprised when arithmetic using F32 and F64 types gives unexpected results. So, that is generally the case. I think, one of the like sort of hallmark examples is when you try to add 0 0.1, 0 0.1, and 0 0.1, and you get like 2.999 infinite repeating or something like that. Dealing with floating points is always, a bit, it's hit or miss, for underlying implementation reasons, right? Programmers unfamiliar with the subject are encouraged to read this Wikipedia article to better understand the theory and trade-offs. Okay, Hare also supports a number of composite types, a few examples of which are shown here. So that would be, let me open up our program here again. So a composite type would be a tuple, technically a string, because that is a multi-byte array, multi-byte slice. Here's a tuple and a struct, array, and a slice. So those are composite types. And composite, so these are primitive, they're built-in types to the language, and string is too. Actually, it's technically a built-in type, but under the hood it's technically not a primitive type. Some of these, there are also a number of more specialized types that are not shown here, such as size, which would be like size t if you're coming from C, and uint pointer, which is pretty self-explanatory. Some of these are introduced later in this tutorial, while others are not useful outside of specialized situations and are left for you to discover when you need them. So this is another reason why I'm writing my book, just so I can, I'm going through the language spec and trying to sort of tease out some of these rules of the language, and I have little example programs to show you this kind of thing. So hopefully this little bit is pretty straightforward. Let's go ahead and continue on. Okay, so here we are on struct and tuple types. Go ahead and type this in or paste this in. Now this does go off the screen. I don't have screen wrapping on. I hope that's okay. I don't want it to like interfere here, but you can see what's going on right here. Okay, structs, or a structure, are one of the composite types supported by Hare. These define a structured value, which is made up of other values in a certain order. In this example, we show two ways of using structs. So first manually, and then by using a user-defined type named chords. Okay, so here's the manual struct. Okay, here's chords that we're creating from this right here. For player 1 and player 2 respectively, we can access the fields of the struct by using the dot operator. So that's right here. Okay, and here's a tuple. So this is how you access tuples. So let's go ahead and break this down. So player 1, this is called an anonymous struct. Let's go ahead and note the type chords declaration above the main function. This defines a type name, chords. So here's how you define your types in Hare, type chords, and it's a structure. And here are the fields. These are called fields. So you have x, which is int, y, which is int. Okay, and we're using that right here. So this is an anonymous struct, it's called. This can be used for any type, not just structs. Uh, so it's talking about the type keyword. Okay, this type is equivalent to the handwritten struct used for player 1 variable. Okay, so these are the same exact thing, basically, except this is defined as a type here. Okay, chords is its own type. Where was I at? But by giving it a name, we can skip the types for each field when creating a variable of that type and reorder them if we so desire. So you see here, we're declaring y before x, or assigning it a value when we create this structure. The other player, player 1, is using an anonymous or unnamed struct type, so that's right here. So it doesn't have a type definition. So generally in C you would see this defined with a type def, okay, with your struct. Player 3 is defined with a tuple type, so that's right here. Here's a tuple. It's a product type, as opposed to a sum type can be one of multiple values. A product type has to define every value within its fields. So, which is very similar to a struct but does not name its fields. They are accessed by their ordinal position. So ordinal is 0, 1, 2, 3, 4, starting from 0 instead of their names. So you can see a struct access here with the dot operator, right? So we're accessing the variable name. You would say player1.x to get this variable, or you would say player2.y to get this value. Now with a tuple, you access it from ordinal position. So starting from 0 index, so you see player3.0 is going to access this first value here, which is of type int. So think of it like this. This fits here, and this 24 fits here. And that's the way you access these, is with their ordinal position. So that's the basics of structs and using the type keyword, and also tuples. You can also create nested tuples if you really wanted to. Um, I doubt you would really need to, but you could. So let's go ahead and just write another quick little program, just sort of starting from scratch so that we can understand the basic underlying syntax and kind of get a little comfortable using structs. Okay, so let's go ahead and write just a really basic program using a struct in order to kind of get the hang of the syntax and declaring one and using one in a function. So let's start by importing the format module so we can print some values to the output. And then we need to define our main function. Excuse me, I need to export that. And let's go ahead and create our struct here. So we would do type, and then this is going to be the name of the struct. Let's act like we're going to create a video game character, and it's going to be a struct. And you can also go like this. Okay, I think this is personally maybe a little more intuitive, especially if you're coming from C, but you could define it more in line like this. That's really just preference. So let's have a name field be of type string. Let's have a lives field be an unsigned 8-bit integer. And let's have health be a U8 also. You know what, let's make this an int just to kind of switch this up a little bit. And you can see that you can use a trailing comma here. Okay, so let's go ahead and create a character. Okay, it's like it's like the very basics of like creating a character if you were making a video game. Okay, so you start with the let, or it can be const, right? Probably let because you're going to be changing these values, right? Lives and health. And then this is going to be the name of the implementation of your struct. So let's do, I guess, Gandalf, right? And it's going to be of type character. And then this is where we would plug in the values. So we'll say name equals Gandalf. And then we'll say lives equal, let's give them 3 lives. And then health is 100, okay, because we're just starting. Okay, now let's go ahead and just print our individual fields, our character stats out to the screen using the, let's use the print format line function. And I'm just going to copy it. So we'll say name, and then you would say to access this field, you would start with whatever your struct is. So we would say Gandalf.name, okay? And then here we'll do lives, and this is going to be Gandalf.lives. And then for health, Gandalf.health. So you use the dot operator to access the fields of your structs. It's the same exact thing in pretty much every language, especially C. So let's go ahead and run this and print our character stats out to the screen. And you can see name, Gandalf, lives 3, health 100. So that's how you declare a basic struct in Hare. Hopefully that's pretty intuitive. If you have any questions, of course, please feel free to put any of that in the comments. So let's go ahead and move on to the next part. Okay, now you should be on the arrays and slices part. Go ahead and type this in or copy and paste this into your editor. So we'll introduce array and slice types next. Array story specific, determined at compile time, number of ordered values of a uniform subtype. So what that's saying is that all the values of your array have to be of the same type. This is considered a subtype of the bigger type, which is the length and the type of the array. Okay. Slices store an arbitrary, determined at runtime, number of ordered values of a uniform type. So same thing with a slice, which this takes a slice here. We're taking a slice right here. These are slices. They have to be uniform values. So you can't have a string and an int and a float in an array or a slice, is basically what that's saying. Now, the length of your array has to be known at compile time, as you can see, determined at compile time, and slices are determined at runtime. So an array may be declared with a specific length and subtype. So here's the length and subtype, and we see right here we're using what's called length inference. So this is inferring the length, and this is going to give us 4 elements of this array. Or may infer the length from context using an underscore. A slice type leaves the length unwritten, and you can see what that looks like. See? Values of a slice or array can be indexed to obtain the value of one or more of their objects, numbered from 0, with the index operator as shown in the samples. So here we're accessing the 4th element of this array because indexes start from 0. That's pretty common in most languages except Lua, probably some other ones. The length, number of items, of an array or slice may be obtained with the built-in len function. So this is a built-in, you can see it, I'm sure it's in operation right here. So this is a runtime assertion. If you're not familiar with assertions, let me try and explain this real quick. An assertion is basically, now you can separate this. In fact, I like to generally separate my functions like that to make it more readable. Um, what an assertion is, it evaluates a condition within the assert block, and if it fails to return true, it's going to abort your program. Okay, so what this is saying is the len of x is 4. That is indeed true. So this program will continue to run. Okay, assert x, the fourth element, which is index 3 here, equals 7. That is indeed true. So this program will run. Now, here's a reassignment. Okay, so we're saying the fourth element, which is 7, we're reassigning it. You see we're using a let binding, so we can change this value. If we declared this as const, we would not be able to do this. We would get a compiler error. So we're reassigning the fourth element to be a value 8. Now we're doing another assertion here. There's also a static assert, right? And that looks like this. That's a static assertion, and that's evaluated at compile time. Okay, so these are assertions. Here we're defining an array. Now what we could do here, let me show you this. What we could do here, I think I showed you this before, we could say buff of type size equals 1024. Now size is like size T and C. Okay, size is like size T and C. This gives you the size of an object, and it is a type. So we could say this, and then we could say buff, right? So let's go ahead and run this program. Okay, so it does compile. And this is a way to avoid magic numbers in your arrays. You generally do not want to have magic numbers in your array. That's, that's an opinion, okay, that I picked up from one of my programming classes in school. I'm sure some programmers would agree with that. Some might not. In any case, though, that I just kind of wanted to show you that. Now, here, this is what's called array initializer syntax. And what this means, what this is doing, so we have an array of 1024 elements, okay, which is a standard, kind of a standard size for a buffer in programming. Not always, but it's common. You'll see it. And it's the subtype is int, so these are integers. So we're actually manually defining the first 4 elements, and then the 5th element and all subsequent elements are going to be initialized with this value. Okay, and you could also use this with strings if you wanted to. You just place your empty string and then initialize that. So this is called array initializer syntax. Okay, like all values, arrays must be initialized when they are declared. This can be awkward for large arrays like y, which is right here. In such cases, the operator, it looks like an ellipsis, is often useful. It assigns all remaining values to the last value. In this example, most of y is initialized to 42. Okay, which again is the answer to life, the universe, and everything. Okay, now here are our slices, and we're going to get into that in the next section. Let's just sort of briefly go over arrays. That this might seem a little bit complicated. Okay, so when you use the underscore, you're inferring the length. Okay, so you have to initialize all of the elements of your array. If, say for example, you were using inferred length and you put and you did something like this, for example, and you were to say 10 and did an array initializer syntax, you're only going to get one element in your array. You're only going to have one element, and then in that case, all of these would fail. Okay, nothing would actually work. So, yeah. Here is the built-in len function, which is very helpful because there isn't one in C. You have to manually get the length of your arrays, and then you can pass that to a function, for example, if you wanted to. But we do have the built-in len function here in Hare. Now again, this is just a runtime assertion, and it tests this condition, and if this condition fails, it's going to crash your program. Here is just a simple reassignment. We're reassigning the fourth element of this array to be 8. And then we're performing another assertion in order to check its value. Here is defining an array. Now, again, here is using def, which is a compile time constant, and we are giving it the value of 1024. It's of type size, and this is the length of our array. You can see here. Now, this is array initializer syntax, and what this is going to do is initialize all the rest of the elements of the array to this value. And since all values have to be initialized at the point of declaration, you're going to be using this a lot in your arrays if you're not automatically plugging in values manually. So hopefully that's pretty understandable. And let's go ahead and move on to the slice types. Okay, so here we are on arrays and slices continued. It's the same exact program, but this next part breaks down things a little bit more, especially with slices. A slicing expression is used to slice arrays and slices with the operator. This creates a new slice which references a subset of the source object. So that's right here. Okay, so we have our array, which is named y, such that y, and then here's the syntax, will produce a slice whose 0th value, so that's your 0th value, your first value, is the second value of y, you see that right here, and whose length is 5 minus 2 equals 3. So this is basically a view, right? You can think of this as a view into this array, okay? Slicing, now this is important here, okay? Slicing does not copy the underlying data, so modifying the items in a slice will modify the underlying array. Okay, so what does that mean? So here, if you leave off the leading index, it starts at 0 automatically. So this is non-inclusive. Okay, so 0, 1, 2, 3. This is going to print 1, 3, 3 if we were to print this, which I think we do. And likewise, if you were to leave this off, this would slice the entire array, okay? But this right here, okay, sorry. Okay, but this right here is exactly equivalent to this right here. When you leave the leading index off, it's going to assume 0. So this specifies the first index, which is inclusive. Okay, so we're starting at the second element, technically the third index, because it's indexed by 0. And we're going all the way to the 8th element, which this is exclusive. So it's not going to include this. It's going to be technically, right, it would technically look something like that, right, because it's only going to the 7th element. So the first element when you define in a slice is inclusive. The last element is exclusive. It's 1 right before it, okay? Hopefully that's understandable. You're just going to have to, play around with slices a little bit to kind of get the hang of them. Now, what are we doing here with print vals? So this is the variable name, and it takes a type of an int slice. Now, this is very handy. When you're defining functions to work with arrays, for example, you're generally going to want to use a slice instead, because with an array, the length is part of its type, technically. So if you wanted to pass an array to this, you'd have to define the length. Well then, guess what? You would only be able to work with an array of that specific size. So generally, what you'll see in idiomatic Hare code is you want to use a slice, which you can also work with both arrays and slices. So let's look, let me kind of, I don't know what I just did there. Let me kind of create some space here, right? To see exactly what we're doing. So we're printing the length of what we're passing in here. That's this right here. Okay. We're passing in this, so 0 to the fourth element excluded, and the second index, technically the third, to the eighth element excluded. Okay, now here's a for loop. This is, hopefully this is not overwhelming at the moment. If you don't want to worry about this right now, we will get into looping later on. Okay, but this is just printing the length, and this is also printing these values. So this is the way you define a for loop in Hare. Now, Hare does support for each loops. Now, what this looks like, this OZ, this is idiomatic Hare. This is what you're going to see as a for loop. Now, because a for loop in Hare technically has type size, so this is just a suffix, and technically what all this is just size, okay? This is actually exactly what a for loop is in Hare. Now notice you do not have the increment operator like you do in C, right? Which is something like you'd see, right, plus plus I, or I plus plus. Well, you can't use that in Hare, okay? So you have this is the way that you have to increment and decrement your loops. And again, so we're just using the length, and we're reading up to the end of it. And again, what you generally will see in Hare is this right here. Okay, so again, that's just, it means type size, and we're just printing the elements in our array. Hopefully this is pretty intuitive. We're printing the index and then the value. Okay, so let's go ahead and run this again. That's already up right here. So you see, for integers, this is the index, and this is the value, and this is our slice. These are both of our slices that we're printing out. So you can see 0, it starts with element 0 and includes 4, but since that's technically the fifth index, it's excluded. So 0, 1, 2, 3, that's right here. Okay, so for this slice, we're starting at index 2, okay, of our array here, okay. So we're starting at index 2, which is going to be 3, and then we're going all the way to 8, which is exclusive. So it's 1 before this. So it's going to print 3, 7, and then 42s. You see that? 3, 7, 42s. Okay. Now, you notice when you take a slice of something, it defines its own 0th index. So when we're taking this slice, right, y of 0 now becomes what y of 2 was. Okay, hopefully that's not confusing. So that is the part on arrays. It looks like we do have a little bit more to cover here, so let's go ahead and get through this part. Accesses to arrays and slices are bounds checked which means that accessing a value beyond the end of their valid objects will cause your program to abort. Now you can see that right here. Okay, we have, this is using length inference and type inference. You can declare arrays like this. This is an array, but you see we're using length and type inference here. We don't have any explicit type annotation. And we are accessing an element off the end of our array here. Now in C, you could do this. You're going to get undefined behavior. But that's one of the great things about Hare is that it has bounds checking. Now you can have unbound arrays, but if you're just starting out with Hare and you're sort of a beginner programmer, don't do that. Just stick with the bound arrays. There's not that much overhead at all. You're not even going to notice it for the types of programs that you're going to be writing. That's really left for, professional developers who are, writing code that they need to be really performant for whatever reason or another. And that's what it tells us here, right? It is occasionally useful but risky to skip the bounds check for interop with code written in other languages, so probably specifically C, or in carefully reviewed code, or in carefully reviewed performance critical code. To do this, you can use a pointer to an array type in place of the array length. So that's right here. Okay, so we're creating an array here, and this is an unbound array that references this array. Now you see what we're actually doing here with now if you were to use X to access the element off the end of this array, it would be bounds checked. This is an unbound array, which is why there's the syntax for it, and it's a reference to X. And you see if you access out of bounds of the array, you're going to get undefined behavior. So it says use this syntax because otherwise we would not be able to determine the size of the required stack allocation. And that means of your unbound array. So default values are still to do. So let's briefly cover this. This is slice syntax right here. Let me pull this program up again. Okay, we are taking a slice here. As we're passing it to the print line function, the print vals function, we're creating a slice that we're actually passing in. You could create this all on its own, but we're creating it as we're passing it in. Okay, what we could do is we could say, let me think of a variable that's not in use here. We'll say let a equal, and then we'll say y 4. Okay, now let's pass in a. Okay, and same thing with this. We'll say let b equal y, and then we'll take a slice of these specific elements, so 2 inclusive, 8 exclusive. Okay, and then we'll pass in b. You see, it's the same exact thing. And so that would be the syntax of how you would say you wanted to have a slice that you wanted to manipulate in a certain way or pass around instead of just creating it to pass to a function specifically. That's the syntax. That would be the way to do it. So that is it for the end of this basic portion here. Okay, if I go back up here, okay, so this video covered all of the Hare basics. Using default values still hasn't been completed yet. I do have a section in my book about default values. So starting in the next video, we are going to be getting into this part right here, which is memory management. So thank you so much for watching. I really appreciate it if you made it to the end of this video. And once I'm finished with this tutorial series, which I'm going to try and get done pretty quick now at this point, we're going to dive into some real world hair code. In my personal opinion, is probably the best example of that is going to be Drew DeVault's repo that he has all of his hair code in, right? He has an operating system written in hair, all kinds of, he has like the, you know, clone of the core utils, things like that. So we're going to get into some real world hair code. We're going to write some programs from like the command line. We're going to deal with opening files and write some like kind of basic command line programs and um, uh, deal with things like memory allocation and some of these things of the language that might not be too clear from just a tutorial. Again, the tutorial and the language spec are at this point the only resources for learning here, which again is why I'm writing my book. So I do have that in a repo. It's not anywhere near being done. Once I get to a point that it is nearly done, I'm going to get feedback on it, and that is going to be available freely online, downloadable as a PDF and an EPUB, and I also have a website I'm trying to put together for it. That's kind of lagging behind the book because it's in a little bit different format, um, and it also has an openly available Creative Commons license, so I'm not charging any money for it or anything like that. I really want to do this in like service to the hair community and try and get a book out there covering some of these things of the language that you'll only know if you read the language spec, which is a learning, it's been a learning journey for me because I had to learn, you know, Bacchus Norform, or what's called EBNF, which is an extended form of it, to kind of understand the context-free grammar. That's what it's written in. The language grammar to understand how the language is constructed, to understand what you can do with the language. So I'll go ahead and wrap this video up. It's probably pretty long, but I'm going to, from here on out, from this point, I'm going to cover each one of these sections in their own entire video. So thank you so much for watching. Thanks for my current subscribers. I really appreciate you sticking around for me not uploading a video in a while. And that's it for now. Thank you so much and have a really nice day.